This video covers a type of building energy modeling called simple box modeling. If you are an architect, a developer, or anyone who's making decisions about building design, then you often face a lot of questions. A simple box model is a tool that may provide some answers. This brief video addresses these questions. What is simple box modeling? When do you do it? Which questions can it answer? What is it good for? Is it accurate? Who does it? And how do you do it? A simple box model is a whole building energy model used to test the impact of fundamental design decisions on energy consumption and peak heating and cooling loads. The appropriate level of detail in the model depends on the state of the design. So during pre-design, the model may look like a simple box, as you see there on the left. And during conceptual design, the model typically represent a simplified version of one or more design concepts. So what makes a building energy model a simple box model? It's simple, it's accurate enough to provide useful information, and it's quick to develop. So these characteristics make it useful for informing early design decisions. This type of analysis is most useful before significant building design decisions have been finalized, typically during conceptual design, but it can also be very useful during pre-design. So a sensitivity study with simple models can provide the design team with useful information to consider when developing design concepts. Later during schematic design, a simple model may still be useful for evaluating design alternatives, like window shading example shown here. What is it not? Well, a simple box model is not the same thing as a shoebox model. And while the terms are sometimes used interchangeably, the common definition of a shoebox model is one that represents an isolated portion of a building, such as a single room, while a simple box model typically represents a whole building. Now, both can be very useful, though a simple box model can be used to answer typically a wider range of design questions. So let's look at a few examples of design questions that might be addressed with a simple box model. What is the impact of window area on energy use or on peak cooling load? So fenestration design is certainly a fundamental design decision. And since simple box modeling can be very quick, it can provide feedback early and while the design concept is still being developed. So another question, which envelope components contribute most to peak cooling load? This information can help optimize the envelope design to focus on investment on components with the most impact. Is it the walls, the roof, window conduction, or window solar? And this info might show that an extra investment in envelope performance, like for better windows, can reduce the load enough to downsize the HVAC system and maybe offset the cost of those better windows. So which energy end uses contribute the most to energy use intensity? So a simple box model can estimate how much the energy is consumed for each end use, like fans, cooling, heating, interior lighting, or plug loads. And this information can be really useful on projects with energy performance goals. It helps to focus attention on the systems that are responsible for the most energy consumption. Another question, which of 3 building massing options provides the best performance? Or a related question, what is the impact of changing orientation? So a simple box model is great for exploring the relative performance of different design concepts like these. How much does the performance vary between these options? Does it make a difference or not? So the simple box model can help answer that question using whatever information is known at the time, like perhaps just the building location and the occupancy type. And then it can show which features have the biggest impact on performance and then which are less important. How about, is this concept design likely to meet the 2030 challenge energy target? That's a question you might face on your design projects. Or a similar related question, can it achieve net zero carbon emissions? A simple box model analysis can help you figure out if your design's on the right track. And if you're not, the model can be used to test changes that might get it there. One important thing to keep in mind when you're asking questions like these, where we want an estimate of the actual future energy consumption, is that a simple box model is quick and simple. And it'll probably be based on lots of assumptions about things like the HVAC system performance and the building operation. So at this stage, this energy estimate is best used for comparing alternatives and finding the best design solution. Then, as the design progresses, it'll be possible to get more confident estimate of total energy consumption and to verify that the design is still on track to meet those performance goals. Another question is, which measures contribute to meeting the energy target? So success in meeting an aggressive target often requires a package of measures. So a set of models with incremental changes can show how much each change contributes to the total savings. So these measures could be things like insulation or window shading, efficient lighting, or HVAC system features, for example. I've shown just a few examples of potential design questions. For more inspiration, check out this resource from the American Institute of Architects, the Architect's Guide to Building Performance. So it has examples of common questions that can be answered using energy modeling and other types of building performance simulation. Simple box modeling, what is it good for? The most common subjects for simple box model analysis are aspects of the architectural design. So things such as the building form or the fenestration design and opaque envelope component specifications. So, what makes it good for these kinds of analyses? Well, they're important, first of all. They affect the thermal loads, which affects HVAC sizing and energy consumption. And second, many of these decisions are made early. So you need a quick, simple method to do the analysis. Third, energy models do a good job at these things. That's what energy simulation programs are really designed for. And fourth, it's hard to evaluate the performance impact of these types of measures except with an energy model. So these are all, relative performance analyses comparing alternatives, which is a great application for energy simulation. Daylight energy savings potential. An energy model is also good for a rough estimate of energy savings potential from daylighting controls. And most simulation programs can estimate indoor daylight illuminance at each hour and adjust the lighting power accordingly. Now, these methods are pretty simple, especially compared to specialized daylighting simulation software. But the methods used by these energy simulation programs are good enough for an estimate of the potential savings. And they also capture the impact on heating and cooling loads. Natural ventilation savings potential. Many simulation programs can also model the impact of natural ventilation, which can be, of course, an effective strategy for space cooling and ventilation in some climates. And natural ventilation calculations depend on a lot of assumptions. And in real life, the performance of natural ventilation often depends on occupant behavior, but this simple analysis can show the savings potential. It might show, for example, the value of an investment in features like operable windows. So this chart shows results of a model with natural ventilation and shows the fraction of the cooling load that can be handled via natural ventilation each month. This chart shows the energy savings potential of using operable windows with an interlock switch to cut off delivery of air. That's one potential natural ventilation strategy. So it cuts off the ventilation or cuts off the HVAC whenever the window's open. Resilience is becoming a more important issue for building designers. So energy modeling programs can be used to provide a rough estimate of space temperature and how that might change when there's a loss of cooling, which might be due to a power outage or system failure. So this illustration shows one hot day, and under normal operation, the HVAC system is turned on in the morning and the space is cooled to a set point. If, for example, cooling is lost at noon, then the space temperature will start to rise, and the rate of change will be different in spaces with low thermal mass and with high thermal mass. So the simulation result can estimate how long the space temperature will remain comfortable in both of those cases. A simple box model can also be used to check if a concept design is on track for net zero energy or net zero carbon emissions. So the model provides the estimate of the electricity and gas consumption, and CO2 emission factors can be used to translate that energy consumption into CO2 emissions. And then a separate calculation can estimate energy production by on-site photovoltaics, for instance, and the corresponding emissions avoided. So this kind of quick early analysis can show, are you on track? Or perhaps you need to find ways to reduce energy consumption or increase the area available for a PV system. Now, simple box modeling is typically performed using the same HVAC system for all cases, but comparative analysis of different system types is possible, and it can be important at an early design stage. So this kind of comparison is especially valuable when considering system choices that affect the architectural design due to different space or structural requirements. So some HVAC system types, like the variable air volume reheat that delivers overhead air, require space for ducts above the ceiling. Other system types, like radiant heating or cooling, can get by with less space because they rely on pipes rather than ducts for distribution. And underfloor air distribution and displacement ventilation work best with higher ceilings and may also affect the floor-to-floor height. It's important to keep in mind that an HVAC comparison does require careful attention to model inputs so that the comparison turns out to be realistic. So it's important that somebody knowledgeable with these systems should be involved in that kind of analysis. To summarize what a simple box modeling analysis is really good for, it's to inform architectural design, to identify high priority strategies, the ones that have the highest or biggest impact, and to track performance versus targets like the 2030 challenge or net zero carbon emissions goals. So how about some questions about simple box modeling? Is it accurate? So building energy simulation programs are quite accurate when we provide accurate inputs. And that's clearly a challenge when creating a simple box model, which is done at a very early stage when many assumptions will be necessary. It's especially useful for comparing alternatives. So the relative performance of different designs is less sensitive to those assumptions we make compared to an estimate of absolute energy consumption, which leads to the final point. It can be useful for absolute energy consumption estimation with good inputs. So who's responsible for simple box modeling? Well, this is, of course, a trick question. In a successful project, there's usually a role for everyone. So design questions. How do you make sure that design questions are relevant? Well, this can't be left to the modeler alone. How about identifying appropriate inputs? The modeler will typically take the lead, but it's extremely valuable to get feedback from the designer and other team members, because remember that we need good inputs for an accurate model. And then who does the modeling and the evaluation? That should be somebody with a strong understanding of the tool and the systems to be evaluated. And then finally, communication and integration. Those are, of course, team efforts and are key for a successful project. So simple box modeling, how do you do it? There's no one right way to perform a simple box model analysis, but here's one perspective. Ideally, start by determining the initial design questions to be evaluated, then identify any specific design constraints, select an energy modeling tool, then identify appropriate model inputs, then develop a base case model, follow that by creating some alternative models, analyze the outputs, present the results, and then iterate or do it all again. Let's start with determining initial design questions. So it's important to spend some time before creating a model in order to list design questions to be explored. Ideally, that list is developed in a collaboration between the modeler and the designers. And it's usually time well spent because it'll help focus the effort on the aspects of the design that are in question. It also helps in choosing an appropriate modeling tool. For example, if understanding potential daylighting savings is important, then a tool that can calculate daylighting performance is also important. So identify design constraints. So there may be constraints to consider when setting up your simple box modeling alternatives, things like height limits or footprint constraints or structural system requirements, steel, wood, or concrete. Adjacent buildings, of course, can have a significant impact, and then owner requirements like access to views may affect where windows need to be located. So the appropriate type of simulation software for simple box modeling is most often a whole building simulation tool, and that will run a full year of hourly or sub-hourly calculations of the thermal loads and then the HVAC system energy consumption. Some of the useful features to look for are automation features that speed up creating simple models, 3D geometry viewing, which helps you ensure your model represents your intent, and availability of defaults. They're especially useful during early design, as long as it's possible to see what inputs are being used. And then the ability to calculate energy costs using time of use, utility rates, and other complex rates can be valuable. And then capability to export your results so that you can create your own tables and graphs to communicate how you wish. And finally, hourly outputs are often very useful for insights into the results. Then identify model inputs. So the overall goal, of course, is to make the model as accurate as we can so that project-specific inputs are the first choice. And this is where input from the design team and the owner is important for success. But on most projects, there's limited project-specific design information available at the time when a simple box model is created. So many of the model inputs will need to be based on typical values or default values. Now, the typical sources of that information are energy codes or other references, and then team experience, and of course, the software defaults. And then also consider prioritizing efforts on researching inputs that are most relevant to the design question being evaluated, because there's almost always a limited amount of time available. So if, for example, the goal is an accurate energy end use intensity estimate, then it'll be important to gather information about likely operating schedules and plug loads and any likely unusual energy end uses, because of course they have a significant impact on the total energy consumption. On the other hand, if the goal is to understand the relative impact of alternatives, like varying building form or window area, then generic operating schedules and internal loads may be fine. So as much as possible, identify project-specific input values rather than rely on defaults. And then highlight and review those most important inputs with the design team. So now we can get to start creating a base case model. So the starting point or the base case, is often a model with code minimum inputs for things like envelope performance and lighting power and HVAC efficiency, but the design team may have other preferences for a starting point, maybe based on a previous design or the firm's typical standard. It doesn't really matter, but typically you choose one starting point. And then, part of the art of creating a simple box model is to make it appropriately simple. So a common approach to thermal zoning is a simplified perimeter core layout. And this approach can also be applied to more complex floor plans. Another common simplification is representing several windows as one large window. That's just an example. And it's often okay to simplify geometry, especially if it'll save time in the analysis. Another element of the art of simple box modeling is defining appropriate alternatives that answer the design questions that were identified earlier. So the alternatives might represent different design concepts, like different options for building form. The alternatives might also cover a range of performance to understand the sensitivity of results to changes in design. So we can find out what makes a big difference and what makes little difference. So this example shows the change in energy use intensity with increasing window-wall ratio. And on the left, the graph shows results that include automatic daylighting control, where you can see the lighting energy decreases as the window area increases. But on the other hand, HVAC energy increases. So the minimum energy consumption is somewhere around 20% window wall ratio in this particular case. And this sensitivity analysis looks at the impact of overhangs for shading windows. And these two graphs show the impact on peak cooling load on the left and energy cost savings on the right. Some alternatives will include packages of measures. So it's often appropriate to evaluate packages, especially when you're looking at strategies to meet an energy consumption target. You will, of course, then need to analyze the outputs, but an important first step when analyzing the outputs is to verify the quality of the model. Even a simple box model presents lots of opportunities for unintended inputs, and an output review checking items like these can help verify the model quality and confirm that it represents your intended inputs. And then analyze the outputs to answer design questions. So pull out the results from the models that are relevant to the question, put them in a table or a narrative, or ideally a picture to answer the question. So that question might be answered with a sensitivity study like this one. What is the impact of window area on energy use intensity? The question might be about different design concepts with questions like, which of 3 building massing options provides the best performance? And this example shows a presentation of results that might be important or useful for making a decision. The analysis might look at detailed output from a single model to answer a question like, which envelope components contribute the most to peak cooling loads? That'll help you focus effort on design to reduce those loads. Or another question is, which end uses contribute the most to energy use intensity? Also, useful question to help you focus your design efforts. The analysis might include the results of adding measures incrementally to a base case to show a path to meeting a target. Or they may show more directly, how much each measure contributes to the total savings. The next to the last step is presenting the results of the analysis. When presenting results to owners and design teams, here are 2 recommendations. First, focus on answering design questions rather than on presenting simulation results. And second, present the information visually. Energy modeling results have little value if decision makers cannot quickly understand them. And finally, the last step is to do it all over again. So the design process, it's rarely linear. As we answer one question, new questions may arise. So allow some time to update the analysis with refined inputs or additional alternatives based on feedback from the design team. And welcome the opportunity to use simple box modeling to play a useful role in the building design process. For more information about simple box modeling and other energy modeling topics, see the wiki at BEMCyclopedia.com.